This is a review video for independence. We'll go over the definition and work through 3 examples, and I'll leave parts of the examples for you to work through. Now for the definition. Now I'm giving it in terms of random variables, but it's similar if I were to give it in terms of events. I use RV for a random variable all over the place. So we say that a set of random variables, x1 through xn, are independent if and only if, for all finite subsets J of the random variables and values in the range of the random variables little xi star, the probability of the intersection of the events that the random variable xi is equal to little xi star for all of the random variables in the subset, and this symbol means intersection, and by this we mean that x1 is equal to little x1 star and x2 is equal to little x2 star and so forth for all the random variables in the set J. This is just equal to the product, and this symbol means product, of the probability of each event happening. So that's xi is equal to little xi star for all the random variables in the set. As you can imagine, this is a very tall order because we have to show that not only does it happen for all of the random variables, we have to show that it happens for all of the subsets of size less than m, such as 3 and 2. Since we often cannot do that, we look at pairwise independence, and by that we mean nearly the same definition, with the only difference being that it need to only hold now for subsets of J of size at most k, so the size is less than or equal to k. Now we're going to work through an example of tossing balls into bins. So we are going to toss, our first example 1 is we're going to toss n balls independently into k bins. And each ball is equally likely to land in each bin. Now the random variable we're going to worry about is actually the bin total. So let bi equal the number of balls in bin I, and I is between 1 and k. So first, as an exercise, calculate what the expected number of balls in any bin is. But now we're going to worry about the independence. So for any bins, I and j, are the bin totals bi and bj independent. Okay, in order to show that they're independent, we're going to try to use conditional probability. So in order to show that they're independent, we'd have to show that the probability that bin I has x balls, given that bin j has y balls, is simply equal to the probability that bin I contains x balls. And we have to show this for any values of x or y. Now we have an example, a quick counterexample to show that this is not the case. So for example, when y is equal to n and x is equal to 1, the probability that bin I contains 1 ball, given that bin j contains n balls, is equal to 0. And That's because there's only n balls, so there's none left to be in bin I, and that's why this probability is 0. So this isn't equal to the probability that bin I has 1 ball. So we've just shown that these bin totals, bin I and bin J, are not independent by showing that knowing what the bin total for bin J is actually does tell you something about the bin total for bin I. So now we're going to look at coin tossing. So we're going to toss a fair coin independently 4 times. And we're going to consider the following events. So event A is that the number of heads is even. B is the event that the number of heads is divisible by 4. And C is that the first toss is a head. Okay, so I've drawn the sample space of tossing 4 coins, and I've highlighted all the events. So the event A, the event that the number of heads is even, I've highlighted in green, I've circled it in green. The event B, that the number of heads is divisible by 4, I circled those 2 points, B and B in red. And then the last event, C, that the first toss is H, I've circled that event C in blue. So now to start, let's figure out what the probability of these events are. So the probability of A equals 1/2, the probability of C equals 1/2, and the probability of B equals 1/8. So now we want to consider, are these events A, B, and C independent? And in order to show independence, we'd have to show that all 3 of them would be independent, and also the pairs of them would be independent. So we're going to start with just the pairs. So the first thing we're going to consider is, are events A and events B independent? So this symbol means independence. So are these 2 events independent? So there's a few ways that we can look at it. So let's consider 2 things. So we're going to consider the probability of A and B, and we are going to consider the probability of A given B. And we can solve them. So the probability of A given B, of A and B, we can look at the chart. So both points B are within A. They're in the intersection. Both of the red points are circled in the green. So there are 2 of those. So that's 2/16. So this is 2/16, which is equal to 1/8. And if we look again at this probability, this does not equal 1/2 times 1/8. So they're not independent. But now let's also look at the definition of conditional probability. So we saw the probability of A and B by looking at the sample space. We know that's 1/8. So, and then if we have to divide the probability of A and B by the probability of B, which we know is 1/8. So this tells us the probability of A given B is equal to 1. You could also use logic to discern that by observing that if the number of heads is divisible by 4, then it would be even. The number of heads would be even also. So we can see that this does not equal the probability of A. So that is another way to show that these 2 events are not independent. So now let's consider the events C and B. So what about C, B? Are these 2 events independent? So let's look quickly at the probability of C and B. And we can look at this in the sample space. So we have the 2 events, B, and then we have C, the blue, And we see that only one of the red events falls within, one of these outcomes falls within the event C. So that's only 1 point, so that's 1/16. So the probability of C and B is 1/16. And if we look at the probability of C, which is 1/2, and the probability of B, which is 1/8, we see that they're equal. Now, as an exercise, consider and show that this is equal to 1/2. Convince yourself of that. There's two ways you can, I want you to look at the definition of conditional probability, but another way to see that is that you see once you know that B happens, you just have these 2 points, and only one of those 2 points falls within C. So that's one way to look at it, but I want you to also just use the definition of conditional probability to convince yourself of this. So C and B are independent events. And then finally, I want you to consider if C and A are independent. And the quickest way is to consider probability A and the probability of C. And I'll give you a hint, they are independent, and you can verify that using the sample space